Okay, so in the previous segment we saw what are the topics we will discuss in the course, and then we started with brief background on ML algorithm. After that we discussed like the history of ML. So, we stopped at spiking architecture. If you remember, spiking architecture tries to mimic the brain, and now we will see the next of spiking, which is nothing but the neural network, and we will see that in the entire course we will build on this topic of neural networks. So, the fundamental block of neural network is known as perceptron, which was proposed by Rosenblatt again back in 1957. So, as you can see, I mean, these topics are not new. So, just because we have like bigger computers, we can actually now implement all these concepts and then see its result, right. So, that is why it's growing more and more popular. However, in literature or like in human knowledge, all the ML algorithm or this neural network type applications were not applications, the algorithms were there in human knowledge. Anyway, so as I was saying, perceptron is the building block of neural network. It's very simple, like inputs multiplied by the weights, they get added, then a nonlinear activation function is applied, and then output is obtained, right. So, let us see how it works. So, let us say we have multiple inputs to the neural network. So, these are the inputs. Now, whenever we say inputs, they are also known as features, right. Now, if you go back to like in the last segment, I was repeatedly talking about the weather prediction task, correct. Now, if you go back and think about that task, now to predict the weather, let us say to predict tomorrow's temperature, you need to know many things of maybe today's temperature or today's weather, maybe some weather, some features of day before yesterday, and so on and so forth, right. So, those are called features. So, let us say you need to know what is the temperature of today, what is the rainfall of today, what is the wind speed, what is the direction of the wind speed. So, if you know all these things, maybe with respect to all these things you can predict or you can estimate tomorrow's temperature, right. Now, all those things which you need to know are known as features. So, this is a very common term in machine learning algorithms. If you do not have features, there will be no machine learning algorithm. So, typically any machine learning algorithm takes some features and then produce the outputs. Now, in this case, as you can see that the perceptron also has some inputs, those inputs are nothing but features, right. And then the features are appended with something called bias, which is nothing but a constant 1, and then we have some weights. So, all these, let us say there are total n features including the constant bias, then if we have n features, then we have to have n weights, okay, or n plus 1 weights in this case from W0 to Wn. We can think the weights are nothing but like they are actually translating how much is the effect of that particular feature. So, let us say in the feature list we have again to predict tomorrow's temperature, we have multiple feature from let us say today as well as day for yesterday, right. So, most likely the effect of today's feature on tomorrow's temperature will be higher than the effect of day for yesterday's feature on tomorrow's temperature, right. So, that is why we have like different weights for different features. Now, all these weights actually get multiplied with the corresponding feature and then they get added. So, in this particular case we will see that W0 multiplied by 1 and then W1 x1 plus W2 x2 till Wn xn will happen. So, they will get multiplied. Now, after the they get multiplied, yes, and then all the product, all the W0 multiplied by 1, then W1 x1, W2 x2 till Wn xn, all the product get added. So, to generate this particular output wherever I am pointing the cursor, right. Now, one very important thing about all this machine learning application or machine learning algorithm is the nonlinear function or the activation function. After we get the sum with all the product from all the weights and all the inputs, then we apply an activation function. Again, this is nothing but a mathematical function. We will discuss what are the different activation function, but overall we need this nonlinearity. This activation function are nonlinear function, like maybe e to the power x, some form of e to the power x, or some form of logarithmic function, and all those things. We need this nonlinearity, because if there is no nonlinearity, then multiple layers of weight times input can be reduced to single layer, right. So, let us say we have multiple of these neurons. So, by the way, this is one perceptron or one neuron. Assume that there are multiple of these perceptrons, and then we are not putting this activation function. So, all the outputs of this sum again get multiplied with another set of weights, and then it produces output. So, in that case, if you like actually do it on pen and paper, you will see that we do not need a separate set of weights. Probably we can fuse all those layers or all those like perceptrons to a single layer, right. So, you can actually this is a take home thinking. It will also be useful for your assignments. You can just do this simple exercise where you do not have some activation function, or I mean anyway we did not discuss about activation function. So, you can forget about activation function. So, instead of just one perceptron, you can have multiple perceptron which takes the same input, but they might have different weights, right. Now, output of all those perceptron again goes to one set of weights, and then you produce the final output. So, you will see the final output is actually a function of all the input, where you can just define one set of perceptron. We do not need multiple perceptron if we do not have the activation function or any nonlinear unit, right. Now, this is the architecture of a perceptron, right. This is another like the example where we have multi-layer perceptron. So, in the previous slide I was showing you just one layer of or one perceptron. I was showing you one particular perceptron where there are multiple inputs are coming, which is getting multiplied by the weights, and then we are getting the output, right. Now, imagine that we do not have just one perceptron, but we have multiple of those perceptron. Okay. Now, whenever we have multiple of those perceptron, they actually form a layer. Let us say we have this input layer. So, input layer is nothing but where the input is primarily coming, and then we have some hidden layers. Now, as you can see that there are multiple neurons. So, we will call these as neurons. So, every neuron is connected with every other neuron in the hidden layer through weights. So, remember, weights are nothing but they are just like some floating point numbers, right, some fractions, some 1.2, 1.3, something like that. They are just some numbers. I mean, they might not be integer, they can be some floating point number, right. Now, again there might be no single hidden layer, there can be multiple hidden layer, and then again from those hidden layer the neurons in the hidden layer again is connected with the neurons in the output layer through the weights, and finally the output layer will provide you the output. We will discuss like how exactly the output is generated and all those things, but this is one generic structure of multi-layer perceptron, and this multi-layer perceptron actually forms the basis of any machine learning algorithm. So, yeah, that is all about that is all about neural networks, but then like for many decades or many years people do lots of research on neural network, and then researchers found that we need to go deep. So, that is where this deep learning came into the picture, right. Now, I showed you one subset of machine learning or some brief history of machine learning, how it evolved, but in the space of machine learning there are different types of learning. So, some are called supervised learning, where we need to learn a model M from labeled input x and y, right. So, again if you go to this weather prediction task, remember that we knew the features, or we knew the weather features of previous day, previous to previous day, and all those things, right. And based on that, we already have some data of few years or maybe few months. Now those known data are called labels. Like for given this feature, we know next day's temperature. So those the features we know, and then we know the corresponding labels, right. So with those features and the labels, we can train a model, we can train a machine learning model, and this particular type of learning is known as supervised learning. Okay. Now not all machine learning model or not all machine learning tasks are similar. There are some example of unsupervised learning also, where clustering, outlier detection comes into the picture. So let us say we have like set of points in the maybe 2 dimensional space, we need to cluster those points based on proximity. So that in that case we can't apply any supervised learning. So it is known as unsupervised learning. Then there is something called generative learning. Most of the recently used LLMs and all those things are come into the domain of generative learning. Then we have something called reinforcement learning, where output is nothing but action and then labels are nothing but reward. Okay. I mean, we will not go into the details, but I mean this is kind of FYI that there are different types of learning. Maybe we will mostly discussed on supervised learning, like the algorithm which takes this supervised learning as its principle. Now, I mean, so far we have discussed like lots of machine learning algorithm and briefly discussed how this multi-layer perceptron work, right. Now at the same time, there are some challenges in computing. Now whenever we say computing, you can imagine we are talking about the computers. So at the end of the day, you can like come up with a very efficient machine learning algorithm, but then it needs to be executed on the computer, right. Other than that, I mean nobody is going to execute all this machine learning application on pen and paper, correct. So we need computers to execute that. Computer means something which can compute. Even your cell phone is also a computer, right. Now in this particular figure, you can see that the x axis is showing as different number of years and the y axis is scaling, where I am showing you 3 lines. One is in gray, one is in green, and one is in blue. The gray line shows the hardware floating point operations for different processors over the past 25 years, or maybe little more than 25 years, right. I think it's around 30 years, correct. As you can, and now whenever someone or some company invents a new processor or brings up a new processor in the market, usually they are measured by the number of floating point operations the processor can perform per second, right. That is the performance of the processor. Okay. Again, floating point operation you can think of like multiplication, addition, something like that. So all those are floating point operations, right. Now the gray line is showing how the processor has, or how the number of floating point operations have increased in the past 25 years, right. And different dots are actually different processor, like you can see Itanium 2, then some TPUs are also there, then this A100 is nothing but the NVIDIA GPU, right. So different dots are different dots corresponding to different processor, and then the gray line is kind of they have shown the trend, right. Now this green line and the blue line shows the DRAM bandwidth and the interconnect bandwidth. Now let us take a step back and discuss how this multi-core processor work, right. So I am sure like many of you are using cell phone or the computer which is equipped with this octa core or the quad core processor, right. Now if you actually open up your computer, I mean don't do it just because I said you, if you actually opened up your computer, you will see that there is a chip, like there is a processor, where if you are using Intel processor, it is on the chip, it is written Intel Core i7, or if you are using AMD, it will be written AMD Ryzen, something like that, right. But we need memory, right. So I mean all of you use computers, so maybe there are like 16 GB, 32 GB. If you use servers, maybe there are like 128 GB or more memory, right. So, that memory is actually separate. So, that is nothing but the DDR3, DDR4 memory, which is sitting separate than the processor. It's in different location in the processor, right. So, that means whenever in any application the processor needs some data, it needs to fetch from the memory. I mean, in general, I mean, I know that you can argue that the data can be in L1, L2 cache, but let us say there is no cache. So, it needs to fetch from the memory first. Also, I mean, not only fetching, whenever the processor generates some data, it needs to store in the memory, correct. Now, remember, this memory transaction happens off chip, right. It needs to go out from the processor, and then it will go to the PCB. There are some wired, metal wired connectivity, and then it will go to the memory, right. So, that happens off chip, and that is a latency consuming as well as energy consuming transaction, because if the data communication happens on the chip, it is not that latency consuming but and energy consuming, but it happens if it is happening off chip, then yeah, it will consume lot of latency as well as lot of energy. That is the thing which is characterized by this DRAM bandwidth. So, as you can see that the processor speed has improved a lot in the past 25 years, but then the DRAM bandwidth has not been improved. DRAM bandwidth means how much data it can take or it can send per unit time. So, that is the bandwidth, right. So, you can see that the hardware floating point operation has been improved 3.1 times per 2 years, but at the same time the DRAM bandwidth has improved only 1.4 times per 2 years. That is one problem. And then you can see that the interconnect bandwidth. So, remember there is an interconnect between the DRAM and the processor. Not only that, there are interconnect on the chip also. Now, remember I was saying that there are some links which takes the data from the processor and then sends to the DRAM. So, not only that, yeah, the links are there, that is the interconnect, they have specific bandwidth. At the same time, there are different protocols also, like this PCIe and NVLink, they are nothing but the interconnect between different processor or the processor and the DRAM, right. So, you can see that the interconnect bandwidth also has not been improved as much as the processor. Now, what it means is our processor can generate lot of data, or it can generate a huge amount of data at like very high speed. However, at the same time the DRAM bandwidth and the interconnect bandwidth is so low, it cannot consume that much, it cannot consume data at that high speed, or the processor requires data at a very high speed, but at the same time DRAM or the interconnect cannot provide the data at that speed, right. So, that is why at the end of 2020, as you can see in this figure, there is a huge gap between this hardware floating point operation of the processor and the DRAM or the interconnect bandwidth, correct. And remember, whenever we talk about this ML application, they actually consume lots of memory. I mean, there are lots of weights. I mean, I am sure you have heard about like billion parameter model. That means it has those billion number of weights. 1 billion weights means it easily will occupy like GBs of spaces, right. Now, whenever let us say you prompt to ChatGPT, then the OpenAI server, all the weights are there. Those weights are actually loaded onto the processor and then some computation happens, right. Now, since DRAM bandwidth or the interconnect bandwidth is low, even if our processor is very fast, we cannot actually utilize that speed of the processor, and that is a challenge in executing the machine learning application or the machine learning algorithms. In this course, we will see many different techniques which actually tries to overcome this challenge. Now, as I was saying that I mean all these processor speed has been improved, but then the DRAM or the interconnect bandwidth has not been improved. That is why there are different accelerators. Accelerators are nothing but they are specialized processors to perform a specific task or group of tasks. Okay. So, in our course we will mainly discuss about the accelerators for convolutional neural network or the large language model or the GCNs, but whenever we talk about accelerators, they are nothing but specialized processor. So, let us say if we talk about DNN accelerators, that means they can only execute DNN algorithm, nothing more than that. It is not like general purpose processor, right. Now, since those accelerators are specific to all these specialized algorithms, that is why they operate in a very high speed, or they are expected to be, they are expected to operate at a high speed, so that they outperform our CPUs, or I mean the state of the art processor, right. So, we will discuss many accelerators in our course, which are in the domain of different machine learning algorithms, right. Now, still I mean memory is a bottleneck, like even if we have accelerators, somebody has to provide the weights or the intermediate data which our machine learning algorithms are generating, somebody has to provide those things or those data to the processor, right. So, still memory is a bottleneck, right. Now, to address that challenge, there are accelerators with emerging technology, which again we will discuss in this course. Like in memory computing or analog in memory computing is one of those technology where you can actually have one particular device, like typically our CPUs or the GPUs are made of CMOS transistors, right. Now, CMOS transistors create all those and or not gates, so that we can compute, and then we have a separate memory which are again made of CMOS transistor, but the property of CMOS transistor, but we use specific property of CMOS transistor, so that they hold some value, that is why they are called memory, right. So far I mean in our traditional or state of the art computers, we have a different processor and then different memory unit. As I was saying that you have a processor where Intel Core i7 or AMD Ryzen 5 is written, and then you have a separate DDR4 or separate memory, right. And I also told you that this transaction from processor to memory is actually costly in terms of latency as well as the energy efficiency, right. Now, to overcome that challenge, there are accelerators with emerging technology, for an example in memory computing, where the device, the transistor I talked about, there are some different types of device or different types of transistor in memory computing, which can perform computation as well as which can act as memory element at the same time. So, if we have those kind of devices, if we perform in memory computing, then we can actually reduce the costly transaction between the processor and the main memory, right. That gives a huge advantage. We will see all those things, but then again the problem is communication will be a bottleneck. Like if we actually store all the weights on the chip with this analog in memory computing, that means there will be so much data going around on the chip itself, right. So, earlier the data were moving from off chip to moving around from the processor to DRAM, but now with this in memory computing technology, communication is a bottleneck. So, we will see some of the technique which are like communication aware accelerator, where there are specific technique to build the hardware, so that the overall communication is less. But then again remember, I just talked about in memory computing, and then I also told that there are some devices which can store the weights. Now, say let us say GPT-3, which has like billions of parameters. Now, if all those weights are actually stored on the chip, then the chip size will be very high. So, if the chip size is very high, then the yield will be low and the fabrication cost will also be very high. So, in that case we have area as the bottleneck. So, that is why there is the fabrication cost aware accelerator, where instead of having like multiple or instead of having a huge monolithic chip, we can have multiple chiplets, so that the fabrication cost is reduced. We will discuss some of these fabrication cost aware accelerator, but the story does not end here, because we have more complex algorithms like graph algorithms, transformer algorithms, And then there are several hardware challenges. We will see, like even if we have accelerator, it is not like that accelerator solve all the problem. There are several hardware challenges like power, fabrication, packaging, etc. So, since we have complex algorithm and then the complex algorithm pose more complex problem in the domain of hardware, we will actually need more and more sophisticated hardware, or we need better technique to build those hardware, so that they can aid machine learning algorithms. So, we will end up deep diving on all these topics in this particular course. So, that is all for this segment. In the next segment, we will actually discuss different architecture of this deep neural network, and then eventually we will go into the topic of convolutional neural network. Thank you.